Hello everyone, welcome to the Verification Lab. This session is on VLSI ASIC design flow with strong focus on RTL design methodology. Today we are going to understand the complete VLSI design flow where the RTL fit into the ASIC lifecycle, industry standard RTL development practices, and open source EDA tool. Before learning RTL deeply, first we need to understand the complete semiconductor design flow because RTL is not one stage in the ASIC development lifecycle. This slide explains complete ASIC design flow from specification to physical implementation. So the entire flow is divided into two parts. First one is front-end design, second one is physical design, also called as back-end design. So first stage is system specification. So in this stage, the engineers define clock frequency, throughput, latency, power budget, area constraint, interface, technology nodes, all these things. Okay, basically this is the requirement definition phase. So if the specification are incorrect, uh, our product may be fail, our power may be exit limit, performance target may not be achieved. Okay, the second stage is architect design. So in architect design, the architecture engineer converts system requirement into hardware planning. Why? These stage decide performance, scalability, parallelism, power efficiency, etc. So the architecture engineer creates data path, FSM structure, pipeline stages, cache hierarchy, memory organization, protocol like AXI, APB interfaces. Okay, so important point is a bad architecture will be extremely difficult to fix later. Okay, then third stage is RTL design. RTL stands for Registers Transfer Level. It describes registers, then the sequential logic, combinational logic, data movement between the registers, all these things. In this stage, we are use HDL language like Verilog, System Verilog, and VHDL. Okay, actually, architecture act as a bridge between a human hardware understanding and silicon implementation. Fine. Then fourth stage is functional verification. In this stage, the verification engineer checks uh, whether RTL behave correctly or not. Okay. How how the verification happen? By using test benches, simulation, assertion, coverages, methodology like UVM, all these things. If the bug discovered after fabrication, it will extremely expensive. So that in industry, in real ASIC project, verification consume nearly 70% of project effort. Okay. And fifth stage is logic synthesis. In this stage, synthesis convert your RTL into gate level netlist. Okay, why? Because the fabrication tool cannot understand the behavior of your RTL design directly. So using synthesis tool, it infer hardware, it will optimize the logic, map logic into the standard cell, okay, and we will get output as a gate level netlist. Okay, then sixth stage is DFT, design for test. In this stage, the additional logic insert for manufacturing testing because the fabricated chip must be testable. So it will test by using scan chain, beast, JTAG, boundary scan. Okay, and seventh stage is STA, static time analysis. In this stage, we are verifying the timing without stimulation to ensure our setup time, hold time, clock constraint are satisfied or not. How? By analyzing delay, clock skew, data path, PVT corners. Fine. Then eighth stage equivalence checking. In this stage, it checks your RTL and synthesis netlist equivalence. Okay, to ensure the synthesis is working properly, or it may different, it functionally getting different. Fine. Then ninth step is floor planning. So the initial physical chip organization. Why? The poor floor planning causes congestion, routing issues. Okay, then timing failures, all these things. So what here the engineers place your SRAM, micros, IO pads, okay, then power grids. So and then tenth stage is your place and route. We can also say placement and routing. Okay, the physical implementation of logic to transform the logic gates into manufacturing layout. How? The tool perform placement, the CTS clock tree synthesize and routing. And 11th stage is DRC LVS. The physical verification checks here to ensure the manufacturability and correctness. How? The DRC check manufacturing rule and LVS check your schematic layout matches or not. Fine. Then 12th stage is parasitic extraction. The extraction of wire resistance and capacitance. At the advanced node, wire delay dominate timing. Okay. Then 13th stage is post layout STA. So what happened in post layout STA? The timing analysis using extracted parasitics. Why? The real routing changed the delay. So how it run the STA rerun using the RC delays. Okay, and interconnect parasitics. Then 14th stage is power and IR drop analysis. The power integrated analysis to avoid voltage drop, EM failure, thermal issues. Okay, how analysis dynamic power, leakage, then your IR drop, migrations, all these things. Fine. Then tape out stage. So in tape out stage, the GDS2. Here in this stage, our chip layout submit to the foundry, because this is the manufacturing database. Okay. Then 16th in fabrication. In this stage, the actual semiconductor manufacturing process, it convert the layout into a transistor, real transistor, by using photolithography, etching, ion implementation, CMP, metal deposition, all these things. At advanced node like 5 nanometer, the billions of transistors exist. The process variation become critical. Then the final and last, sorry, second last stage is packaging and ATA testing. So in this stage, the chip packing and production testing to ensure the fabricated chip functionally corrected by including the process like wafer bonding, wire bonding, flip clip packaging, automated testing, equipment testing, all these things. And last is post silicon validation. The real silicon bring up and debugging. Why some bugs appear only real hardware. That's why the team perform silicon validation, thermal testing, power characterization, performing tuning, debug. Okay, if the major bug found, the silicon may respin, so the cost may reach millions of dollars. Okay, now that we understand the complete ASIC life cycle. Okay, so these are the roles, responsibility, and skills requirement. Okay, for RTL design, what is the responsibility of RTL design? Write synthesizable Verilog or system Verilog code and ensure the logic and functionality will be okay. Okay, and what skill required? HDL coding, digital design principles, synthesis aware coding techniques, all these things. Fine. Now Let's focus deeply on our RTL design because RTL is the core of front-end VLSI engineering. Okay, so what is RTL? It stands for register level, register transfer level. Okay, it describes how data move between registers, sequential logic behavior, combinational logic behavior, and clock hardware operations, all these things. Okay, when you write your code, okay, the register become flip flop, your if else block become mux, okay, and your arithmetic operation will become adder or multiplier, such that your FSM block become state machine. Okay, so why this RTL exists? Because RTL is the language used to describe digital hardware before the synthesis. Okay, and how it works? Using HDL languages like Verilog, System Verilog, and HDL. Fine. And one more thing, the timing. One more thing is the RTL is different than software. Why? The software executes sequentially, where the RTL all hardware block operate simultaneously. Okay, so open source tool in the RTL flow. This is the foundational module of our RTL to synthesis journey. If you write some Verilog code and simulate basic circuit, then you are ready to go next step. This module bridge bridge the gap between your code and actual chip, creating actual chip. Fine. So first is RTL coding. So recently we discussed about RTL code. Okay, now we see simulation. What is simulation? Before moving forward, you need confident that your RTL code is actually work as per your functionality. Okay, so this is you this is where the simulation come in. By using tool like iVerilog, Verilator, then or commercial tools. Okay, you can execute your HDL code with test input and observe the output. Fine. Then second is lint checking. So what is linting? Linting is the static code analysis process that flags the potential hardware debug, your syntax violations, and non-synthesizable structure without executing or stimulating your RTL. Okay, it evaluates your code against the strict industry standard rules to ensure the design can be safely translated into physical hardware during the synthesis. Fine. For that, we are using a Verilator tool. Okay. Then next is CDC. CDC is clock domain crossing. The modern chip contain multiple clocks. It may cause metastability. Fine. So what happened? The flip-flop enter undefined state. Why? The asynchronous signal violate setup time and hold time. Okay. The fourth is synthesis. So, synthesis is the automated process of converting your RTL into technology specified gate level netlist. Right? It acts as a crucial bridge between the software like hardware coding and physical layout. It continuously optimizing the circuit to meet the strict power, performance, and area. PPA constraint, we say that. Okay, so if you can join our course, so what you learn in the course is RTL coding styles, good coding practices, then FSM design techniques, linting, CDC, synthesis flow, debugging RTL issues. Okay, all these things we will cover in our course. Now here I am taking one example of pattern detector by using Murray machine. Fine. So it will show the flow from RTL to synthesis. okay, and it will show how tools are working. So for simulation I'm going to use iVerilog. I will first simulate my design. Okay, my design. Also I am give my test bench. Fine. Also I am creating one output file. Okay, then I will run. So my design is compiled and simulate. Now, uh, now I have to verify is my design is working functionally correct or not. Okay, you remember that I'm create here one out file. So I will run this file. Fine. So VVP Verilog virtual processor. So I am running this file out. So what happened in this process? Your test bench is executed sequentially. Okay, see here my test cases are passes. This one is first test case, second test case, third test case, fourth test case. Okay, all are passing. Fine. Now I now I want to see uh, waveforms. So how can I see the waveforms? When I run this sim out, okay, in I give in my test bench that .vcd file. So it will create a .vcd file. Okay, tb.vcd. First, GTK wave. In GTK wave, we will see the waveforms. Okay, tb.vcd. So here you can see this is the test bench, and under this here is our design. So I will take signal of my test bench and I will append. Now you see here in out, here I got my pattern. So it will show 1. Here also I got my pattern. Here also I got my pattern. Okay. After that, what? My design is working fine without any error and without any warnings. Functionally it is working clear. But then also I have to need to check lint. Okay. For that I am using Verilator. Verilator. Okay. What I give here extension that lint only and my design. Okay, I run. My design is lint free. Okay, after linting, synthesis. So I will do synthesis of my design. Fine. For that I'm going to use Yosis tool. I'm invoking my tool here. Okay, I invoke. I just this is flag, passing flag. Okay, here I will read my Verilog file. Okay, pattern detector and synth. Okay, also I will give my top name of my design. So this is my top name of my design. Okay, and that. Fine. Here I am using SV, so I will give the extension here hyphen SV. Fine. Now I run. So synthesis is completed. Okay. And I also told you that whatever you write in RTL, it will convert it into gate like NOT gate, NOR gate, all these things. Same thing happen here. Today we understood complete ASIC flow, RTL fundamental, simulation, linting, CDC, synthesis, uh, all these things. Okay. Uh, Also, if you can join our course, you will learn digital electronics, CMOS, Verilog, Linux. We will teach basic Linux command, CDC, and linting. We will also cover FPGA flow, STA synthesis also, and we will take project. Okay, so hope you will join this course. And if you master in RTL, then you can design CPU, AI accelerators, FPGA system, communication hardware, custom IC, ASIC designs, all these things. Okay, thank you everyone.